Hi folks, this is Roger from Wave Computation Technologies. In this tutorial, I'm going to explain how to use the transient simulation to obtain a smooth spectrum response. Okay, so before I do that, I need to explain several concepts about transient simulation. Mainly, I will explain this part in the Design tab in the Time setup. There is two options on the time window. So this is telling you how long will the transient solver solve the electromagnetic field. So you see there's two options, exclusively. One is user-defined, the other is automatic. So this is how telling the solver how the user want to determine the simulation to be stopped. For example, for the first one, if user-defined, you can just say the unit is nanosecond. You just tell them 2 nanoseconds, 3 nano, 5 nano, 1000 nanosecond. That's it. Then when the time window is reached there, it just stops no matter what. Okay. Even if your signal is not zero or is still radiating or things like that, that's it. It's a firm line that need to be met. Okay. The other is automatic. So there are two parameters over here. This is measured in dB. One is called energy decay. The other is called energy variation. So as I said in the text, energy decay will be the magnitude. For example, your initial pulse magnitude is 1. Then when the signal magnitude reaches about 10,000 times smaller, that means E1 e to the minus 4, then that means, okay, this criteria is met, and the simulation will stop. The next thing will be energy variation. This is different than the energy decay. This is the variation. That means, okay, your initial energy variation is from -1 to +1. So that the magnitude is 2, right? You see that. So when the energy change, the waveform change, is smaller than -80 dB, which means 1 e to the minus 4 times smaller, then this criteria is met. Whichever comes first, the simulation will stop. Okay, so it's either telling you that your energy is totally gone, everything decays to 0, you stop the simulation, or you reach a steady state that nothing is going to change in your computational domain, then the simulation will stop. Okay, so that's about these things. So if you're only interested in the transient results, for example, the time domain signals, snapshots in time domains, I mean, you don't need these two parameters. You only user define at the initial time. That's fine. You can see everything already. But the important thing is, if you want to take a look at the spectrum response, sometimes user-defined time window is not sufficient to obtain a good result in spectrum. Okay, so I'll explain why through a example. Okay, so let's take a look at over here. This is the example, very simple. It's just a microstrip line. Okay, transmission line. I designed it with 50 ohm already, so you can see this with a PEC ground. Okay, and there is a substrate. You can take a look. It's actually, I changed the transparency, but if I change it to be smaller, you will see, okay, there's a substrate underneath it. The material is RT Druid, and this is a material parameter, relative permittivity. Okay, so as simple as that. This is designed to be 50 ohm. So I created 2 lump ports at 2 terminals. You take a look at the source resistance. In the source part is the 10 ohms only. It's not matched. It's definitely not matched. Okay, 50 ohm is the matched ones. So this one is 10 ohms, and then on the receiving part, this one is 5,000 ohms. So that looks like I did this purposely. Let me explain this. I want the signal to come out, and here it almost looks like an open circuit, so that signal will mostly reflect it back. And when it reached to this one, because this is 10 ohm, this is 50 ohm, another reflection will be generated. So you can imagine if I give a pulse, it will be coming back here and there and here and there, just to keep resonating between, bouncing back and forth, back and forth. And of course, each time it will be attenuated a little for two reasons. Number one, it's the energy is consumed by this 10 ohm and 50 ohm a little bit. And the other thing is the leak. Okay, the field will leak out as the radiation part, but because that radiation will be very weak according to this case. The main energy is still be consumed by the resistance. Okay, so that's how you understand this problem, and you want to see the similar phenomena. And I want to demonstrate why the time window is so important in obtaining the spectrum response correctly. Okay, user-defined automatic is quite different. So let me start the simulation. So as you can see, the simulation is started. It's very quick. And then if I pause it, so this means, okay, the simulation only stopped at 0.2 nanoseconds, only 588 timestamps. Okay, and the nice feature about this software, about the transient simulation, is you can already see the result. So two things I want to take a look. Number one is the scattered voltage. Okay, it's here. Number two is the S11 parameters. Okay. So I put the two results over here. I move this a little downward here so everybody can see everything. So here's the thing. This is the voltage transient time domain signal. This is the spectrum response. Okay, S11 parameter reflection coefficient of port 1. So if I continue this simulation, let it go, keep going, then I stop it. Okay, so you can see, okay, I have some signals, but this is all the transient data I can obtain. And at the end, the signal is not even turned to 0. So there will be definitely a cut. And then in the FFT, the frequency spectrum response, it takes the transient signal suddenly jump to 0. And that causes a lot of high frequency thing. So if you take a look at the result of the S parameters, you will see, whoa, it's definitely not reasonable. You have a positive values. How can that be, right? This is pure passive network. It goes to up to 0. This is just because your time domain result is not sufficient. So you need to continue. Okay. So just let it run for a longer time. You can see, okay, you have more transient data coming in. As I said, it's reflected and decay a little bit, consumed by the resistance. And now you can see, observe the frequency spectrum response according to this type of transient signal. You begin to see some reasonable things about the sink. That means energy is radiated or is resonant at that frequency, right? But a lot of ripples, high frequency ripples, is coming in. Why? It's just because it's not terminating correctly yet. Now you see it's decaying really fast, right? And then it returns to 0. But actually, it's still not 0 yet. Okay? As you can see the result. Alright, so it's keep going. Now it's getting better. Everything below to 0. That makes sense now. But you still see the ripples, right? Over here. And this part is much better. Better smooth things. So you just keep going. And now you see, okay, now it's good. This one is smooth enough. Everything is below 0. And the energy is almost 0 compared to the original magnitude, right? Of course, if you zoom in, you will still see that it's definitely it's still resonating. But the value is already very tiny. It's about only, it's almost 0 there. So it's very small. So all in all, this means in order to obtain a smooth and reasonable spectrum response in the transient simulation, you need to guarantee that your transient signal start from 0 and always decay to a steady state. Okay, it doesn't have to be to a 0, but it has to be very small variation over there, so that your transient signal is smooth enough. After the FFT, you get a reasonable result. Okay, so that's all about this tutorial. Thank you for being my audience.